Okay, geometry, we are in Chapter 4, Section 6, Triangle Congruence, ASA, AAS, and HL. Pause, come back when you're ready. So, AC and BC are legs, and AB is the hypotenuse. The side between angle A and C, segment AC. And the third angles theorem. Today we will apply ASA, AAS, and HL to construct triangles and to solve problems. We will also use these postulates to prove triangles are congruent. So one thing we need to know is how a orienteering works. So let's think about this. Participants in an orienteering race use a map and a compass to find their way to checkpoints along an unfamiliar course. Directions are given by bearings, which are based on compass headings. For example, to travel along the bearing south, 43 degrees east, you face south, straight south, and then you turn 43 degrees to the east. Okay, so here's a little compass I grabbed so we can look at this. Remember, when we want to know the orientation, usually we'll start with north being straight toward the top, right? South is 180 degrees in the opposite direction, so it's usually down. West is to the left, and east is to the right when we're looking at a map with the north up, right? So think about the United States. In the west we have California, right? And in the east we would have New York. So for this heading again, we would face straight south, and then we would turn using a protractor 43 degrees from south. So this would be 0. We'd go 10, 20, 30, 43 degrees to the east, toward the east side, and we would head exactly that way. Okay? Good. So we're going to use that later in the lesson. In the meantime, we have a common side of two consecutive angles in a polygon. So if we look at angle P, it's made of PR and PQ. And if we look at angle Q, it's made of QP and QR. These two angles, P and Q, share a side. That side is PQ. It is called the included side. It is the side included in both of these angles. Okay, so we have a postulate involving this included side. If two angles and the included side of one triangle are congruent to two angles and the included side of another triangle, which means two angles and the side between them, right? Then the two triangles are congruent. So look at this. We have angles A and D, congruent. We have side AC and DF, congruent. And then we have angle C and F, congruent. So angle, side, angle is congruent to angle, side, angle. And so we can say the two triangles are congruent. This is called the angle, side, angle congruence postulate. Let's think about this problem. We're going to have to draw a picture here. A mailman has to collect mail from mailboxes at 3 points, actually 2 points, A and B, and drop it off at the post office at C. Does the table give enough information to determine the location of the mailboxes and the post office? Okay, so we have three angles given, or we have three directions given, bearings given, I guess, and so we can form angles. We have AB, the segment AB would be found if we just face north and then turn 65 degrees east. Going from A to B is a distance of 8 miles, so we know that side, right? And then we would go from B to C by starting at B, where we ended up in this first case, and facing due north and turning 24 degrees to the west. And then finally we would, from C, face due south and go 20 degrees to the west. So to answer this, it really is best to take the information, so here's the listed information, and plot this down. So, I've got a lot of things written here. So let me kind of pull this apart. the first thing we want to do is just, we would start with a vertical line straight up, so a line that points north-south. And we learned that going from A to B, let's look at it again, A to B is north 65 degrees east. So we just make a line and we find a point A. That's going to be our starting point, point A. And we're going to put our protractor there. I'm going to have to spin it around because we're going to the east, right? Which is to the right. So let's see, we start here. I'm going to have to shift it over a little bit so it's right on A. Okay, so there's my protractor right on A. And again, it says to face due north and then travel 65 degrees east, or point 65 degrees east. I feel like I need to move over a little bit more. Let's see here. Okay, so here we have facing due north from A, and we look at 0, 10, 20, 30, 40, 50, 60, and 65 degrees. So we bring that point B down a little bit. Whoops. Let me get that out of here. Point B down a little bit, 65 degrees. And we then just pull that away and draw a ray from A straight out to B, through B. Okay? We know that ultimately this length is going to be how many miles? And we were told B is 8 miles. Okay? So, whoops. Okay, from B, so let's say we measured this and we said that was 8. So from B, it says we are to go to C, north 24 degrees west. So we're going to draw that line through B. So that's what this line is for. Okay, going north and south. And this time we're going to go to the west. I'm going to spin this protractor around and place it right on, place the center point right there on top of B. And again, to check, 24 degrees west. So west is to the left, right? So as we look up the protractor, we need to go from the 0. Here's the 0 here. So 10, 20, and 4. Okay? Am I right on? Hey, whoops. When I did this last year, I think I was doing it on the board with the students. So let me make sure this is right on. So 24, 20, and 4. Let me grab a pen. And 10, 20, 24 is about right here, right? Okay, so that's going to be my point C. And we would draw a line from B. Let me move the protractor off. A ray starting at B and going right through. Here's the point, right? Right through point C, like that. Now we don't know how long it is, so we just extend that ray out, kind of pointing to infinity. Our last ray is starting at C, right? C. And from C to A, we have south 20 degrees west. Okay, so we're going to start at C and go south. I don't know exactly where to place this, but south would be straight down, right? And 20 degrees to the west. I feel like in order for it to hit my A, I'm going to have to go further up on my coordinate plane. So let me just make the ray here because I have my guideline, this vertical line, and we're going to go from that point 20 degrees to the west. Okay, let me get this off of here. Now, notice that we're not hitting A with this ray. So if I simply slide this up the line, it should still be 20 degrees, right? Right up my guideline until I get to the ray crossing the vertex A. I should still have a, let me bring my guideline up. Okay, and I should still have a 20-degree angle from my guideline. So let's see, check it out here. And yes, this ray is coming 20 degrees toward the west as I bear south. Okay, so very good. Now, looks like this vertex C isn't quite where my line is, but you have the idea. It's probably a little bit easier to do on paper. This line, if it's not perfect, we should be just about on this guideline. So a little hard to work with on this smart board, but you have the idea. So just given the bearing of these different sides, right, we are able to show where the 3 points are in this question. Okay, and the question was, could we determine the location of the two mailboxes and the post office C? And we kind of did by using a triangle, creating a triangle, post office and the two mailboxes. So the question that is being solved here, the measure of angle CAB, let's look at that, CAB, see that, CAB, is 65 degrees, remember we turned that direction 65, and subtract the 20 degrees, and that's the 20 degrees that we have here, right? So CAB gives us 45 degrees. The measure of CBA, let's see, CBA, this angle right here, would be 180 degrees. Oops. So imagine the line, and we subtract 24 plus the 65 degrees. So you know the measures of angle CAB and CBA, and the length of the included side AB. So by ASA we have a unique triangle. We haven't proved it to be congruent to anything, but we do have a unique triangle. Okay, that 180, we subtracted this angle here, 24, and this angle here, the 65, which was the alternate interior angle to our original angle A. Okay? Boy, okay. Let's move on to some actual practical triangles to get you the feel for using ASA with a given example like this. So can we use ASA to prove these two triangles are congruent? Let's look. What do we know? We know that this angle here and this angle here are congruent. We also know that we have a second pair of congruent angles in these two triangles. So the question is, do we have a side, an included side, in this example? They both share this side, don't they? Now, is that the side between the two known congruent angles? Nope, it's not. So we have an angle, and then a side. So this is not ASA. We can't prove it to be congruent by ASA. We can use a third angles theorem to prove another congruence relationship based on ASA. And this theorem is called angle, side. Okay, so notice that the side in this theorem is not the included side, a side that both of these angles share. If two angles in a non-included side of one triangle are congruent to corresponding angles and non-included side of a second triangle, then the two triangles are congruent. This is called, as you saw, the AAS congruence theorem. Okay, let's try proving this. We're given that angle G is congruent to K and angle J is congruent to M. That's just given. We also know that angle H is congruent to angle L. That wasn't given. How do we know that? Remember? Very good. The third angles theorem. HJ is congruent to LM, and that also was given. Okay, so now we can say triangle GHJ is congruent to KLM, and that is by ASA. We know H and L are congruent, so we have ASA. Let's use AAS to prove the triangle's congruent. So we'll start with given. We have angle ZY is supplementary to angle YZW. ZY is supplementary to YZW. Okay, they form a linear pair, don't they? Definition of supplementary angles. We know that angle VWY is supplementary. VWY is supplementary to YWZ, and there we have another linear pair, don't we? Definition of supplementary angles. We know that angle XZW is congruent to YWZ. That was given, okay? And this all points to angle YZX is congruent to YWV. Okay, and that's by supplementary congruent supplements theorem. So if this angle is congruent to XZY, and YWV is congruent to ZWY, then we know that YZX is congruent to YWV. Okay, and we also have two other given things. We have angle X is congruent to V, and segment XY is congruent to VY. Those are given. So with that, we can say that triangle XYZ is congruent to triangle VYW, and that is because we have angle, side. So I can get you back up there. Angle, side. Given angle, and side. Okay, why don't you try this? Try to prove this and come back and check your work. I'm just going to show you the answer because we're going so long today. You can pause and see if your proof is like this. Now if you did a 2-column proof, that's fine. Just compare it to this. In the end, we start with given and we move to the proof. Okay? We have a final theorem today, and it is called the hypotenuse leg, HL, congruence theorem. If the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and a leg of another right triangle, then the triangles are congruent. All you need is a hypotenuse and one leg. Can you use the HL congruence theorem to prove these two triangles congruent? If not, tell what else you need to know. So we have, look at that, we have these two sides. Are those the legs or the hypotenuse? Yep, they're both hypotenuse. And then all we need is a leg. Do we have a leg we know is from each triangle that is congruent to the other? And we do, don't we? We have a shared leg. So we can use the hypotenuse leg theorem to prove congruency here. How about here? And in this case, we have two legs that are congruent, and we simply need to know, are those hypotenuse congruent? And do we know that they are? We really don't, huh? So we cannot prove them to be congruent triangles, these two, because we don't know whether there are a pair of congruent legs. Can we use the HL congruence theorem to prove these two triangles to be congruent? What can we say about AC and BD? Yep, they are hypotenuse, aren't they? And do we also know a leg that is congruent? And we do, because they share leg BC. So yes, we can use HL to prove that these two triangles are congruent. We would say ABC is congruent to DCB. Remember that when you name them, you must name corresponding angles in these two polygons. Okay, and come back and check your work. Number 1, ASA. Number 2, HL. And number 3, we have either SAS or SSS. And I'm going to show you this real quick so that you can understand how that proof is made. And here you go. Long lesson. Enjoy your assignment.